Hello everyone, and welcome to my video on Lagrange error bound. So in class, we talked about the alternating series estimation theorem, and the idea of this theorem is that it allows us to determine what the maximum error is, what the absolute error would be, between perhaps the actual sum of a series and any partial sum that we do to it. And we know that we saw from this that the error can be no greater than the very first excluded term of your particular alternating series. But as I mentioned in class, right, not every series is alternating. So what do? Well, this is where Lagrange error bound will come into play. So you may recall the function e to the x and its Maclaurin series, right? It was every power of x. So that started at 1 because that's x to the 0. And then we had plus x, and then x squared over 2 factorial, right? And then x to the third over 3 factorial, and so on, right? So that was our Maclaurin series for e to the x. And right, this Maclaurin series is not alternating, so we can't really use that alternating series estimation theorem. The other thing I should say that we didn't necessarily actually perform is we didn't determine the actual interval convergence for the Maclaurin series of e to the x, but as with sine and its Maclaurin series, you can verify by using the absolute ratio test that the interval convergence for Maclaurin series for e is all real numbers. So we can plug in any number into this Maclaurin series to get a value for e to that number. And in particular, to demonstrate how Lagrange error bound works, I'm going to choose x equals to 1 to show you how this crazy Lagrange error bound actually functions. So, as mentioned, I'm going to let x equal to 1, consider x equals to 1. And so e to the first power, well, that's just the same thing as e. And we know e is roughly, right, it's roughly 2.718, 281828, and so on, right? Right, it was the Andrew Jackson number that I had mentioned earlier this year. And so, okay, that's great. And that's what the value for e is. But how, like with the alternating series estimation theorem, right, we know we can't add up an infinite number of terms here. So how do we know like how far we may have to go out on this Maclaurin series to perhaps get the proper decimal accuracy to this value for e to the first power? So I'm going to start off perhaps just trying to look at certain degree polynomials and of this Maclaurin series here that we have for e to the x and kind of examine what's happening there. And I'm going to start off with the second degree Maclaurin polynomial. So if we consider a second degree Maclaurin polynomial, that would be for e to the x, that would be maybe 1 plus x squared over 2 factorial. And we want to use this second degree Maclaurin polynomial to approximate the first power. So we'll plug in 1 for x into that polynomial, and we'll have 1 plus 1 squared, which is 1, over 2 factorial. And, right, any finite number of terms, we can always add that up, and that's roughly 2.5. Now, if we were to consider the difference between this approximation and perhaps the exact value for e that we see here with these digits, right, that difference there, it's going to be 2.718 minus this 2.5. That difference would be 0.218281828, and so on. Okay, so that's the actual difference that we see there between, again, the approximation and the actual value for e. Now, recall again the alternating series estimation theorem says that, again, the error between an approximation and the actual sum is no greater than the very first excluded term. So if we were to perhaps consider, all right, we use this second degree polynomial here. We plugged in 1 to approximate e to the first power. What would be the very first excluded term from this approximation? Well, that would be the term that we would get when we plug in 1 into this term right over here, x cubed over 3, because that would be the very first term excluded from the second degree polynomial calculation. And so that very first excluded term would be 1 over 3 factorial, right? It's, again, I plug in 1 for x here. 1 cubed is 1, and sorry, that should be 3 factorial there. I missed that. 4. But right, this here is the very first excluded term from this polynomial. And when we calculate 1 over 3 factorial, right, that's 1 over 6, and that particular value is 0.16 repeating. So okay, that's the actual value of the very first excluded term here. But unfortunately, when we look at that and compare it to the actual error, this isn't larger than that actual error. So we can't say, oh, just look at the very first term and that's going to be greater than the actual difference, because that's not happening here. So that's no good, right? Now, to expedite this process for the next couple examples, oops, I just sped right through that. I'm going to look at graphical representations of certain degree polynomials, what e to the first value may be, and what the actual difference is. So to highlight what I just did here, algebraic or computational wise, what is on this slide here are 3 different graphs. The green graph is the actual graph of e to the x. The blue graph, in this case here, is the second degree polynomial that's being used here, second degree Maclaurin polynomial. And the red graph is the actual difference between e to the x and our second degree polynomial. But since we're trying to approximate at x equals to 1, right, what is specifically e to the first power, this red graph right here, this point at 1, highlights what the exact difference is between e and our second degree polynomial at x equals 1. And we saw that that, again, was this 0.218218, all right? And that wasn't good enough. I should say the first excluded term isn't good enough, isn't large enough to cover that particular difference, to give us a comfort that that's going to allow us to know what the absolute error would be when performing these approximations. All right, so all right, that was the second degree polynomial. If you look at this for higher degree polynomials, here is again the same sort of setup, e to the x's graph. Now this is the third degree Maclaurin polynomial, and the red graph being the difference between the two at x equals to 1, the actual error between e to the first and our third degree polynomial at 1 is this 0.0516, so on. And if we were to then take the very first excluded term from this particular polynomial, this third degree polynomial, that would be x to the 4th over 4 factorial. And when we plug in when we plug in 1 into that x to the 4th over 4 factorial, we get 1 over 4 factorial, which would be equal to 1 over 24. And as a decimal, 1 over 24 is 0.0416 repeating. And unfortunately, once again, this 0.0416 is less than the actual error. Again, that first excluded term not giving us the comfort level to know what our, an upper bound to this error. So this is no good. Move on now to the 4th degree Maclaurin polynomial for e, and look at specifically here at x equals to 1, the difference between e to the first and the approximation found when we plug in 1 into the 4th degree Maclaurin polynomial. This is the actual difference. It's 0.009948, so on. If we once again examine the very first excluded term from this 4th degree polynomial, that would be 1 to the 5th power, which is just 1 over 5 factorial. And that's the same as like 1 over 120. And that value is 0.0083 repeating. So unfortunately, once again, this first excluded term is less than the actual error, and that's no good. So I'm going to magically do something in here, adjust things ever so much so that when I make this adjustment, we're going to have an upper bound to the absolute error that we're seeing in each of these examples. So going back to this first approximation, the second degree polynomial, first excluded term was just 1 over 3 factorial. If we were to multiply that by 3 and get 3 over 3 factorial, well, 3 over 3 factorial is the same as 1/2, and that would equal 0.5. And when we compare that to the actual error, hopefully we agree that that now is bigger than the actual error. So this 0.5 would be an upper bound, an upper bound, not the best upper bound, but an upper bound to this error. We would know that our error has to be less than 0.5, which in this case, I mean, we know it definitely is. Go to the third degree approximation. This was the very first excluded term, 1 over 4 factorial. If we multiply that by 3, we get 3 over 4 factorial, which is 1 over 24. Sorry, which is 1 over 8. And that's equivalent to 0.125. Compare that to the actual error, and 0.125, once again, it's greater than the actual error. So this would be an upper bound, not the best, but an upper bound for that particular actual error. So, wow, we're magically coming up with these values that can be used as an upper bound to the actual error. So once again, go to this last example here, the fourth degree polynomial. This first excluded term, no good, wasn't bigger than the actual error. But once again, if we multiply that by 3, we get 3 over 5 factorial. And 3 over 5 factorial, if we actually do that calculation, we get that that is equal to 0.025, which 0.025, once again, is greater than the actual error. So I'm now going to show you what Lagrange error essentially is. But I will say that it does involve, sort of, in a way, the very first excluded term from any particular approximation that's done. Whatever approximation, whatever polynomial you're using, this very first excluded term from that approximation is sort of used to help us come up with this upper bound. So, in order to do these calculations, so this is what I'm gonna refer you to, because whenever we come up with a polynomial, technically we could have always used the Taylor polynomial, which can be used even for the Maclaurin polynomial. Right? This is the formula that we have to construct that polynomial. And if it's an nth degree Taylor polynomial, right, the general structure of every single term is what this is here, right? We have x minus c to the nth power, we have the nth root of f, a value at the center point, and that's all over n factorial, right? That's the general structure to our Taylor polynomial for each particular term. So, find that once again. So here's the Lagrange error bound, or sometimes referred to as the remainder estimation theorem. It says, okay, given that you have y equals to f of x, and it can be differentiated n plus 1 times on an interval containing the number c. And this n plus first derivative at x is less than or equal to some value of m in absolute value for all x on the interval. Then this goes on to say that your error, the absolute error, the difference between the actual sum and your approximation, can be no greater than, well, if you look at this here, structurally, it hopefully resembles the general structure of how we construct our Taylor polynomial formula. If we're talking about, x to the n plus first power, where we subtract c from the next value, right? The coefficient there is over n plus 1 factorial, and the numerator here is normally just the n plus first derivative of f at the center point. So this is the major adjustment that we see here. Perhaps that's different than that construction Taylor polynomial in the sense that we're not going to evaluate the n plus first derivative at the center point. We have to sort of determine what is the maximum value and upper bound for the n plus first derivative of the function on a particular given interval. And so this is the Lagrange error bound. When you try to utilize this, I would say it's similar to the alternating series estimation theorem in the sense that you can kind of go towards the very first excluded term. You can kind of use the Taylor polynomial formula to kind of set things up. And essentially, you have to be able to kind of identify then what is your n, what is the x, what is your center point, and then lastly, try to get at what that m value would be. So in the example, in each of these other examples, how I kind of came up magically with that number 3 and the whole big setup there, well, okay, we start off with the function e to the x. And I'm just going to write down actually my little formula here. Right, this is, again, the structure of Lagrange error bound, that the error can be no greater than this particular setup here, but you can remember this setup essentially from the Taylor polynomial formula, just remembering that m is still related to the n plus first derivative of f, but we got to examine it on an interval. So, okay, we have our function, which was e to the x, step by step. If we start off I start off with the second degree polynomial, n plus 1, n being, again, the power of x, which would correspond to the respective derivative. Well, x plus 1 here would be 3, or n plus 1 would be 3 because second degree polynomial would mean n is 2, and we had 1, so that we get 3. So that's what n will be when we set this up. X, it's kind of where, we're evaluating the function at, and we were examining e to the first power, so x was 1. C, that is the center point of our particular series and polynomial, and we were dealing with the Maclaurin series and Maclaurin polynomials, so C is just 0. So we now know what n is, what n plus 1 is, I should say, what x is, what c is, and we know what n plus 1 is. So now what we need to consider is, what is f, the n plus first derivative of f, which n plus 1 being 3. So what is the third derivative of f? Well, we know the derivative of e to the x is always itself, so the third derivative of f is just e to the x. And now we have to consider that particular n plus first derivative on a particular interval. And it's already hard enough as it is, and this is where it gets even weirder and crazier. But for this particular problem, the interval that we would consider perhaps, we know that this polynomial is a Maclaurin polynomial, so we are evaluating things, at or around 0. And we were trying to approximate e to the first power. So the interval on the other side, we would go up or consider using that polynomial to evaluate things up to x equals to 1. And so it is this interval from 0 to 1 that we can look for a upper bound to this third derivative on this particular interval. Again, because one endpoint is the center endpoint, and the other one is where we're evaluating things at. And that's one way to come up with these intervals. Now, for an upper bound to e to the x on this interval, one thing to note about, or to remember about e to the x, is that it is always increasing, right? So if that is the case, the maximum value to e to the x on this interval, we should be able to find that on the right side of the interval because, right, e is always increasing. So m, we could have said, well, m is just e to the first power, and e to the first power is roughly 2.7. But again, it has to be an upper bound. It doesn't have to be the least upper bound, but it has to be some upper bound, some value that we know every single value of this third derivative is going to be less than in magnitude on that interval. And so hopefully we'd agree that 3 would be an upper bound, right? E to the x will not be larger than 3 on that entire interval. And so for that second degree polynomial, when I came up with that magical 3, that's where I was getting that number from, right? And if this was just a problem in a vacuum, to set up what the upper bound would be to using the second degree Maclaurin polynomial to approximate e to the x at x equals to 1, I would just now plug in everything that I found here into this particular formula to get an upper bound, right? And so, right, our m, we said was 3. Technically, if you really want to say m could have been 100, it could have been 1,000, it could have been a million, but that's not great upper bound. This 3 is a very good upper bound. And then n plus 1 was 3, so that's over 3 factorial. In absolute value, x was 1, the center point was 0, so it was 0, and n plus 1 again was 3. And this is going to be equal to essentially 3 over 3 factorial, right? And that was that value of 1/2. That definitely was an upper bound to that second degree polynomial. And then how I came about multiplying each of the other first excluded terms from the third degree polynomial and the fourth degree polynomial, when I work those out, the thing about e to the x, right, is we know is that any respective derivative of e to the x is itself. So as an upper bound for each respective derivative, 3 would always be an upper bound. And then from there, that's why I knew just multiplying each of those first excluded terms from the approximations would give us that upper bound, right? Because it would follow this Lagrange error bound formula. So this is very, very difficult. If you do see this on the AP exam, you do your best. If you try to remember it as, again, Lagrange error bound is essentially the first excluded term from my polynomial, with the exception being that when you try to set up, right, you can use your Taylor polynomial formula, right, to sort of set things up, right? If we're going up to the nth, we have an nth polynomial here. The very first excluded term would be essentially this, once again, with n plus 1 plugged in for n. But that numerator there, you have to sort of think about it as, got to find an upper bound to that respective n plus first derivative on an interval. And usually the best interval that you can choose, it's not provided to you, is where you're evaluating the function at and where's the center point of your polynomial. So hope that helps. If you do come across Lagrange error bound on the AP exam, and if you have any further questions, you can feel free to ask me in class. Thank you for watching my video, everyone, and I hope you have an awesome day. Take care.